Hello everyone, this is Mariem Bouafif. I'm assistant professor and a researcher at the Signal, Images and Information Technologies Laboratory at Manar University. Today I'm going to introduce our paper entitled Evaluation of Zero Frequency Filtering Based Method for Multi-Pitch Streaming of Concurrent Speech Signals. This work was performed in collaboration with Professor Tom Bäckström from Aalto University, Finland, and Professor Zied Lachiri from Manar University, Tunisia. Let me start with a high-level summary of this work. So what is multi-pitch streamer? It is to stream pitch contours of multiple target speakers into different pitch trajectories over the entire mixture, involving unvoiced and silenced discontinuities. Why do we need a multi-pitch streamer? Because it improves pitch separation performance on overlapped speech drastically. How does it work? It takes a multi-speaker score channel signal as input and uses a zero-frequency filtering to detect all involved excitation components from which it estimates their pitches. So before talking about the pitch streamer, let's do a quick recap of our speech separation method, which we presented at ICAST 2016. The problem we are solving is known as the cocktail party problem, where multiple talkers are speaking and you only want to listen to one person. That's easy for the human auditory system, but difficult for machine. Usual used source separation algorithms are categorized as multi-channel or single-channel. We already developed a blind source separation algorithm, which is a blind two-channel solution in which we don't know the number of sources. We introduced to our system a localization algorithm which estimates the number of speakers and their time delay. Once the source's excitation components were detected, each speaker is separated using the time delay predetermined information. And these excitation components are segregated, then used to synthesize a separated speech estimation. When evaluated on the signal separation evaluation campaign, our preliminary system was able to be improved unless we enhanced the pitch streamer. So since zero frequency filtering algorithm was developed for the analysis of speech, it has been widely employed for both epoch extraction and pitch estimation. So we take one step forward in the present work and propose to study the feasibility of using zero frequency filtering inside the pitch streamer for a multiple talker context. Multi-pitch analysis has given rise for a wide variety of methods. Most of them perform at the estimation level. Particularly for speech, the multi-speech context has been addressed in different works. Many other algorithms address the tracking level. However, few studies have investigated the streaming level. Especially for the multiple speakers context, a supervised method is proposed based on factorial hidden Markov. Recently, an unsupervised method has been developed and used for the separation task. Moreover, the latest general and unsupervised constraint clustering approach, which explores the different timbre features for speech. This method does not require pre-training. However, it requires a prior knowledge of the number of sources. The objective of this study is to examine the feasibility of using a zero-frequency filtering approach to address the streaming level. Since zero-frequency filtering was developed for the analysis of speech, it has been widely employed for both epoch extraction and pitch estimation. So recently, a discriminative technique to separate speaker excitation features in two-speaker mixture is used to generate a pitch track to each interfering source, showing the case of one and two speakers. It was expected that the proposed approach will be accurate even for more than two speakers. A zero-frequency filter-based technique for voiced and unvoiced discrimination has also been investigated and performed under noisy conditions. These two works motivate us to study the feasibility of using zero-frequency filter for multi-talker streaming system, which streams estimated pitches over the entire conversation. In our multi-pitch streamer, we extend the tracking algorithm for a variable number of speakers. Then we incorporate a voice activity detector to reach the streaming level. This step up should allow our new approach to cope robustly with long utterances containing both voiced and unvoiced portions. As summarized in the flowchart illustrated figure, the proposed system can be divided into four main steps. The first step is preprocessing of the observed mixture to enhance epochs of involved speakers. The second step is the number of involved speakers and their time delay estimation. The third step is epochic segregation and pitch estimation at the frame level. And the final step is the streaming of the trajectory of each involved speaker in the multi-channel speaker. Now, the first step is preprocessing. It consists of creating a new version of observed mixtures to enhance the excitation components, then facilitate their extraction. Each observed mixture is independently processed by using multiple functions. Since experimental evaluation indicated very epoch extraction by using the Hilbert envelope of the linear prediction residual of a speech signal, rather than applying it on the signal itself, particularly in the multi-talker context, then the Hilbert envelope of the LP residual is applied on both observed mixture. Moreover, a Gabor filter on LP residual is also used for epoch strength increasing. The second step consists of extracting one of the key features of the proposed approach, which is the localization information to guide pitch streaming. Referring to the speaker's time delay, the excitation information corresponding to each speaker could be separated. For that, a TD-way approach was developed and tested in a last work. The number of speakers and their time delay are synthesized over a cross-correlation function between the modified and preprocessed Hilbert envelope of the LP residual of the two observed mixture. In the third step, the excitation components corresponding to a specific target source are enhanced by a channel time delay alignment, which makes the desired source's excitation components in coherence, whereas the competing speaker's excitation components will be in incoherence. Finally, speaker epochs are derived by applying a zero-frequency filter on the post-processed signal. This procedure is iteratively repeated to determine all speakers' epoch sequences until the estimated number of sources in the mixture is reached. The result of this process is a sequence of epochs for each involved candidate over the entire mixture. The primary use of the detected epochs associated to each candidate for each frame is the instantaneous pitch estimation. As a speech signal can involve unvoiced and silenced discontinuities, such regions should be identified to stream the detected pitch all over the entire signal. As the regions of glottal activity are more significant in voiced regions than in unvoiced ones, detected epochs can be used as an aid for making voicing decisions by referring to their peak intensity. The voicing and voiced regions clustering is further validated based on the pitch period and the instantaneous jitter measured at each epoch. Only epochs with pitch period less than 15 milliseconds and a jitter within 1 millisecond are considered as voiced. After voiced and voiced decision, all instantaneous pitch values are simply identified, then concatenated and viewed as one continuous pitch stream in the detected voiced regions as shown in this figure. For our co-channel multi-speech pitch streaming evaluation, one of the greatest difficulties is the lack of high-quality pitch referenced dataset. In the field of speech separation, there is a blind source separation stereo recorded dataset with multi-speech content, making possible the localization and source counting task for the proposed approach. Selected mixture contain 2 and 3 sources of the same gender and recorded under varying reverberation times. Our optimal channel distance was set to 1 meter to ensure accurate TD-way results. Streaming evaluation requires reference pitch streams. However, used mixtures are without provided ground truth pitch values. Therefore, we generate our own auto-labeled pitch values of the original clean speech, which are subsequently used for the performance evaluation as ground truth pitch values. To measure progress, streamed speakers' pitches are evaluated using 5 metrics: deletion and insertion error rates, gross and fine error rates, overall errors, and the global accuracy. To evaluate the effect of preprocessing, we computed the accuracies, the gross errors, and the fine errors for three conditions by applying zero frequency filter on the observed unprocessed co-channel signal, then on the Hilbert envelope of the LP residual signal, and on the preprocessed signal. We performed the simplest case where we have only two concurrent speakers. This figure reports accuracies, gross errors, and fine errors averaged over 10 mixture. It shows that even if fine errors are very similar for all input signal versions, the preprocessing is beneficial in terms of gross error. Consequently, significant improvement of accuracy with more than 15% is performed by preprocessing the observed mixture. These results show that preprocessing the signal plays an important role in improving the performance of the algorithm. It could be questioned whether or not the zero-frequency filter-based approach is adequate in the presence of realistic reverberation. For that, we study the effect of varying reverberation time conditions on the performed accuracy in two-speaker case. In this figure, we note that, unsurprisingly, the proposed algorithm is subject to large decreases in accuracy as reverberation increases. It is essentially due to insertion errors increasing with the reverberation, which affects epoch detection accuracy by inserting extra false peaks. Another performance evaluation is conducted by comparing the proposed algorithm with a single-channel constraint clustering algorithm referenced as Douan's approach. The code is applied on a randomized channel. Experiments are conducted for the case of 2 and 3 sources. In this table, we report detailed error rates averaged over 10 mixtures recorded under low reverberation time. We can note that the number of insertion errors in the case of 2 speakers and 3 speakers mixtures is significantly high compared to deletion error rates. A preliminary study revealed that these errors are essentially due to Bayesian time delay estimation affecting sources epoch segregation. Moreover, there are regions in speech where one speaker is dominated by the other, making incorrect pitch detection. We can also remark that our algorithm yields the gross error from insertion errors in voiced frames. Even if that error is considerably high, voiced and unvoiced regions detection is probably done, and it can be moreover ensured by the small deletion error rates. We add that very close results are not set all over mixtures for every type of error. We can also obviously note that contrary to the suggested approach, Douan's algorithm performance shows 0% of deletion errors, however, considerably high insertion errors are noted. We note that using the same gender of speakers makes speech trajectories interfere with each other, and many masked links constraints imposed by Douan's algorithm by consequence are incorrect and lead subsequently to large insertion errors. Even if we outperform Douan's algorithm, it is worth to note that 47% of accuracy is still not satisfying. Introducing additional preprocessing stages may be a possible way to overcome the reverberation effect. Such issue is quite challenging for the Douan algorithm even at low reverberation. That was my talk. Thanks for your attention and feel free to ask your question. Thank you.